This is coming from a project that has had 3 different National Science Foundation grants and 25 papers, primarily in the field of engineering organization. So this is project engineering around construction. And we've stumbled upon a problem that I think is relevant for many of us working in the fields of information and communication. One of the challenges is we're increasingly finding ourselves in a data-driven society, and yet data need good teams. That the production, circulation, and reception of data, big data, data science, data analytics, in my case, 2 different kinds of engineering analytics. Did we just lose my?
No.
Okay, good.
Got it to a good level.
No.
Thank you. I don't want to blast you all. So these are problems of how do you get the last mile of data science? How are we getting data analytics integrated into team decision making? This is, I think, for our side of the world, an MP problem, right? This is a pretty wicked hard problem. We know that there's a galloping forth, a speeding train of increasing reliance on multiple streams of data from different kinds of sources. How do teams understand and manage this? And especially, as we'll hear from these 2 cases that I'll talk about today, across different disciplines. So when teams are working with people from different perspectives, different backgrounds, different disciplinary approaches to data, how do they make that data sensible across those teams? So if you can't tell already, my work, I am trained as a sociologist, and my work has been around the emergence of new communication technologies, broadly speaking. And I work in the institutional and social levels of analysis. So I'm not a behavioralist. I don't look at individual behavior, but I do deep qualitative research on the ways in which industries, companies, and practices are changing over time in relationship to these technologies. So I'm going to give you my takeaway, and then you can zone out for the rest of the talk and do email. Data really have this potential to remake the terms of collaboration. And I think that potential is on both cognitive and institutional levels. So to get to that point, you have to understand that data, and again, I'm looking at engineering data, very specific engineering analysis data. Data are always fundamentally social and communicative in nature. That is one of my key assumptions going into these projects. It's produced through systems of meaning making and tools of mediation. So for the communication studies folks in the room, this will immediately look recognizable as to what we think of as communication, right? So I'm basically claiming that the stuff of our lives, right, large-scale data is fundamentally a communication practice. And I mean this in part because data require conveying intended meanings through a process of encoding and encoding, transmission, reception, interpretation, and that we need to be bringing these tools that we have from social science and communication and information studies in particular to understanding these practices, right? So I think that this is where we get to real transformation in the ways that we look at what teams do with data, when, and why. But before I jump into the project I'll spend the most time about, I want to give a plug for the new book and show you the link between these projects. So with funding from Intel, I spent 3 years looking at how a new kind of data, the emergence of consumer wearables for health, wellness, and activity tracking, were like smartphones that we all have and carry with us. I'm trying to make you feel better. But we are all wearing these devices. We either carry a smartphone, we wear some kind of wearable. These devices are generating new kinds of data that have the potential to challenge institutions, relationships, and the processes of sense making. In this particular context, I went around to doctors 5 years ago and said, so doctor, what are you going to do when someone brings you information from a consumer biosensing device? And they said, huh? And I said, well, you know, when your smartphone can give you information about your health. And they said, for what condition? For every social scientist and every technologist that was part of our study and our work, they were like, what do you mean, what condition? Like, well, you know, being human and having an iWatch, having an Apple Watch, that's a condition, right? So what we found in this project is the ways in which the expectations people had for their data in the healthcare setting was fundamentally and wildly varying across the different groups of stakeholders. Patients wanted one thing, technology designers wanted something else. Doctors considered data as having the potential for yet a third thing. And so these different valences, we call them in a paper that was published early last year, these different valences really often have conflict that comes into play when you see the intersection at these different institutional levels. So what this book is, and why I'm not bringing it to you all today, and why I'm happy to talk about it at the end of today's talk, is this new book that's coming out next month with MIT is really a primer geared for non-experts, so for undergraduate students, for the general public, about what's at stake with the widespread collection, reflection, analysis, communities, and sense-making around what might be called quantified self-data, the data that we choose to gather about ourselves and why and when that data appear. So this idea that data isn't just this natural thing out there that's found, that actually decisions are made to collect it, decisions are made to design devices for it, is part of what informs the work that I'll talk to you today. So essentially, the argument is, when does data make sense to people? And my answer to that question would say it always depends on a set of social contexts and a set of social relationships. This is another context. This is the greenest commercial office building in the world. It is the Bullitt Center in Seattle. And to say that it's green is an understatement. It's 100% renewable on-site energy, 100% renewable on-site water, 100% renewable on-site waste management. So this is a net zero building as a commercial office building. It was built as a research prototype by an environmental foundation, and it houses the University of Washington's Building Science Lab, where some of my collaborators and students work. Our students actually helped work on this building. It's been featured in the New York Times. It is the cutting edge of building science. And yet, how did the architect responsible for this building describe what it took to get there? He said, it was as innovative in its design process as in its materials, that it took a detour away from a traditionally very linear process to get an extraordinary team working together from the very start of this building. So, you know, this idea that it is this team targeting the seemingly impossible together right from the start. Every decision made about this building had to be run through a multidisciplinary process. So if you see these gorgeous wood beams, the building is unlike most contemporary buildings. It's not made from steel and concrete. It's made from a wood structure, which hasn't been used in the United States for the last 100 years. So how do you get a modern building, a modern office building, to meet contemporary fire standards and be made of a renewable resource in timber, which the Pacific Northwest is very handy in? Those large windows have automatic sensor-controlled, computer-controlled ventilation and lighting diffusion to allow for, again, a net zero building. So this takes no energy off the grid. It takes no plumbing off the grid. It contributes no waste to the city waste. So this building shows what's possible when multidisciplinary teams work together. It shows what's possible when an architect, an engineer, and construction professionals start to plan their work very early. And it's only possible to reach these kinds of again, cutting edge of our building science capacity. It's only possible to get there with sophisticated analytics. What we've been doing for the last 3 years is studying the energy analytics and how teams integrate those into decision-making processes. Unfortunately, they don't often work as well as this project. So we know that we have the capacity to get teams to integrate data-driven insights into their design decision-making, but in reality, most teams fall short of this. And they fall short for several reasons. Engineers are often not trained to communicate in teams in these particular ways. But then neither have we, as people concerned with informatics and communication, neither have we focused on these dynamics of what's unique and different about teams working with data in these multidisciplinary settings. What is it that they need for problem solving? And I would present for you today that this is kind of fundamentally different. So, as I said, this comes from a series of papers. We've had about 25 papers that have come out of these 3 NSF projects, and now we are in the process of writing this through the book. And one of the challenges that we found, and I'll tell you about these images represent 3 of the 4 types of teams that we've studied. One of the challenges that we find that's consistent across the teams is that they actually need very different things from their data in order to spark their multidisciplinary or cross-disciplinary collaborations and problem solving. So let me walk you through these 3 types of teams. The first in the upper left-hand corner is the first type of team we studied, which is those a little closer to the construction phase of a building. This is in the final stages of the design and the beginning stages of construction in a process called the MEP coordination process, for mechanical, electrical, and plumbing process coordination process. And it's where literally these different kinds of companies who will be installing the systems that run our lights and run the plumbing in buildings will work together to make sure their systems will all fit in the small space that architects allow them to have. So we sit in this very comfortable room, but we do not see the wires connecting the electricity or the speaker system wires or the plumbing that is going through here or the HVAC, the heating and cooling that's going through this building. We don't see any of those systems present in this building, even though they're clearly here because we're comfortable and it's a working, functional room. So that's the work that we spent 3 years studying just those teams. Then we were lucky enough from the National Science Foundation to study the process of the way digital transformations were changing that process throughout the whole design and construction process, where we followed one complex construction process of a laboratory building from schematic design all the way through construction. The second kind of team was a group of student teams on a VOS, a Virtual Organizations of Socio-Technical Systems grant. And these student teams were doing the same kind of construction problems and design problems, but they were in avatar space. So these were students, this was a special built project in the Unity platform. And the students for several iterations have been in a collaboration between the University of Washington, Finland, India, and Virginia Tech. So these are big global teams doing many of the same problems and challenges that we see in the professional teams. We'll talk a little bit more about the visualization you see on their screen there and the ways in which those teams needed to work. And then finally, the final kind of team that we've studied is the way that energy modelers are coming in to inform architects for design decisions. So this is a newly emerging kind of analytics, and architects are really grappling with the implications of how to make sense of this data for their own design. The big takeaway here is that data visualizations are more about simply communicating what the data is. Data visualizations are a launching point for how these cross-disciplinary teams like to work. Let me bring in, to contextualize this, let me bring in kind of 4 touch points for our literature. I promise not to walk you through the methods of each of those 25 studies that we've done out of these grants. And I promise not to bore you with literature, but I want to give you a few concepts as touch points. Louis Bucciarelli, in a beautiful book called Engineering Design, has a beautiful way that he talks about what happens in the process of design. What happens is the social negotiation actually falls away. Like what we see in the end product of design is not the process of design. That there's a big difference when you get teams working together through the process of negotiation. The end product almost always masks that. And so there's this wonderful tradition that is inspired by his work through thinking about engineering design that's been very important for our project. Catherine Henderson in 1999, the classic Online and on Paper, made this argument about the cognitive affordances of paper, the way in which, well, we just think differently when we're sketching. And what she argued is that these sketches become conscription devices, right? They become these ways that the designs themselves actually become part of the organization of the design. And that's been hugely important for the way we've thought about our work. Jennifer Teshy's new book, if you haven't read it, I highly recommend it, Seen Like a Rover. She makes this beautiful point that the visualizations for Mars rover's teams, for those scientists, weren't just representing the science. They are the science. That is, when teams of cross-disciplinary scientists start doing the nitty-gritty of producing the visualizations, that is when they're doing science. And so these really challenge her findings, and I would say those of Bucciarelli as well. They really challenge the way that we think about data visualizations and representations as being distinct or separate from the work of the team, rather than being deeply imbricated in that. That brings us to the last. Paul Leonardi, Diane Bailey, Vonda Orlikowski, and a whole host of others have thought about the relationship between materiality and organizing, or technology and organizing. That you can't really say that you have one without the other. That the role of socio-materiality within technology and within organizations means that when new kinds of technology or new kinds of data emerge, that certain organizational practices may be sticky and others may be more ready to change. The challenge for researchers is knowing which one and where. So what we take from this theory background is to understand that the needs of collaboration and cross-disciplinary teams is actually quite distinct from, say, teams within one company of one single function, right? Engineers, architects, and construction professionals are relying on these kinds of visual media to actually try to both communicate what they see as problems, but to solve them together. It should be no surprise then that when we change the medium of that communication, when we change a 2,000-year-old communication strategy in construction, they might have some challenges integrating that into their teaming processes. So here's a point that for the construction professionals is somewhat shocking, and for all of you will seem absolutely obvious. And yet I think the implication is quite important for the way we talk about the integration of large-scale analytics into decision-making. In the teams that we studied, they've been working in this process called building information modeling, and that's what you see on the left. That's a building information model of building systems. That's a heating and cooling system, and a plumbing system, and a water system, and a few electrical conduits in that geometric space. These kinds of systems have been used to help plan the construction to make it more efficient earlier in the process. So it's been seen that the engineers have the data from these systems and these models, and that they bring a certain kind of expertise from the ways in which they evaluate their particular engineering problem, be it engineering analysis, structural analysis, or in the case of these would be mechanical analyses. Okay. However, these visualizations change the way that teams come to solutions. So the visualizations become what people talk about. The engineers may bring the data and the expertise to the room, but the teams are the ones that are actually having to integrate and make actionable the insights from those problems. So the typical teams that we studied looked much more like the ones on the right. What should strike you about this team on the right is there's a guy wearing personal protection wear. There's someone wearing a safety vest, right? This is someone who clearly goes back and forth between the construction site and rooms that look a lot like this, which are the planning rooms for a construction firm. So what did the introduction of building information modeling do to this field? Well, digital design was not new when building information modeling started rolling out in the early 2000s. Architects and engineers have been doing 3D CAD design for quite some time. What is new is the ability to integrate multiple kinds of analysis into one software package. So just imagine, I like to call it CAD on steroids, which may seem inappropriate, but that's what I do. That's what I call it. It is a process of interoperability that is new here. It is that a structural engineer and a civil engineer and an architect and a construction planner now have the capacity to take their specialized software packages and integrate them into one visualization. This is pretty new to the industry, right? It's so new that this is a screenshot from the first multinational construction firm to ever roll it out. So we were there at the beginning 8 years ago when the industry was starting to grapple with how they're going to work with these visualizations. And the first problem is that it makes problems much more explicit. The 3D geometries and the smart database-driven modeling of the software mean that every object in these digital models is potentially smart. So you could click on it and see if that particular item had been ordered from the warehouse. You could potentially click on it and see which particular model number of the furnace has been ordered or approved. You could click on it and see where it is in the approval process. So it can be an information management system for these distributed teams. However, one of the things that the construction industry has found very useful about these is simply the 3D geometries. Literally, you can see if a pipe is hitting another pipe, and they don't want to see those, right? You don't want your, excuse my crassness, you don't want your freshwater pipes to be hitting your sewage pipes and intersecting in the wrong way, right? And if you can solve those problems before you get out into the construction site, the industry believes that you can have more efficient, faster construction, fewer costs, more benefits, everybody's happier. However, and here's the big however for our field, the problems are easier to see within these 3D geometries, and it's been harder for the teams to solve them compared to what they were doing before. Why is that, and what can be done about it? One of the problems is the problem of interpretive and cognitive flexibility. On the left, you see what an architect or a builder would call a plan, what we might call a blueprint. The two-dimensional, paper-based description of what a building should look like. Most of us, though, can't imagine that 3D space as well as an architect and engineer can. On the right is the building that 2D schematic is showing. And both of these buildings, this is the school, this is the architectural hall at the University of Washington, the building where that houses the Department of Construction Management, where my collaborator works. So when we're talking about 3D buildings, we can see the process of the building much easier. We can see some things more apparently. And yet, to the trained visual thinker, we're stripping away some of the interpretive flexibility from the two-dimensional models. That is, when presented with a two-dimensional representation, every architect, builder, and engineer immediately mentally translate those models into three-dimensional space. And it's quite generative space. They begin to think about the building in a cognitive way that gives them the capacity to generate new ideas. When we see the model in 3 dimensions, we have less interpretive flexibility and thus less ability to generate new ideas. However, there's another problem. What color are the windows in the representation on the left? And what color are the windows in the representation on the right? This building doesn't actually have purple windows, but because you see in a 3-dimensional model a color, you can begin to think that that is a decision, that this is actually a brown and purple building. It's actually white with very nondescript window framing, right? As models get documented, this process of documentation is important for the teams to be able to have some grounds for collaboration and discussion, but it strips away the possibilities of interpretation. So not only is the move from 2-dimensional to 3-dimensional models changing the nature of the cognitive flexibility of the model, but it also, there's a process of the documentation of as soon as design decisions are documented, then certain things get inscribed into the teaming process. We'll talk more about that in just a moment. These have big impacts because these visualizations move in very different ways across the teams. So when I'm talking about a large-scale laboratory building, it took 2 full years to design and construct this building, complex laboratory building in an unnamed Pacific Northwest city for science that we call Lakeside Lab. A complex 40-story high-rise building with mixed-use residential and commercial, and then a 9-story full city block-sized complex hospital building. So these kinds of buildings take millions of dollars, teams of close to 1,000, and they have many different moving elements. So these data are moving across teams in very different ways, across people that need different things from the information. Time and again, what we found in the teams that we looked at is that they challenged these ways that the data could move, but the expertise or the context behind those data decisions could not. And I'm happy to tell one of the stories that we have in one of our papers about the decision, about one of the decisions to make that more explicit. So what this means is that we noticed in both student teams, professional teams, and in avatar teams that the process of problem discovery and the process of problem innovation or problem solution were actually very, very different processes. Notice what's happening on the right. Yes, they're all looking at their computer screens. Yes, there's a visualization up on the board, but they're kind of like leaned back. They're actually looking at and talking to one another. They need a different kind of communication medium in order to help them brainstorm the solutions to the problem that are embedded into the, or displayed by the medium that they see digitally. So this kind of understanding problem discovery and problem solution or problem innovation as separate stages actually helped us think radically differently about how the data were changing the process of construction. So for example, on the right, on the left you see a professional team, on the right you see one of our student teams. There's avatars somewhere in the space from Virginia Tech, Utrecht, and University of Washington. So literally coming together around a visualization was powerfully and fundamentally significant across these multiple types of teams. literally showing people what the problems were in the visualization, helped bridge these disciplinary gaps in understanding. So constructors, construction professionals, could understand what the engineers were saying when they were able to see these quick and rapidly produced visualizations. The same happened with teams of students who had less expertise in this field. So they're able to quickly come to some kind of shared understanding across the group by literally looking together. They look together at the model, and then even in a digital space, in an avatar space, the two women are looking at the same thing. They're looking at the same problematic wall in their design in avatar space. However, when it comes to thinking about how to come up with solutions to those design, you need to move from what we're talking the process of shared understanding through messy talk to having a communication medium that is malleable for resolution. And this is one of the challenges that we found with these new three-dimensional models in construction, that the models did not have the capacities to quickly and rapidly allow teams to iterate or prototype around them. You see here, in both cases, one of the teams of professionals on the left and the student teams in avatar space on the right, they went for abstractions and things that they could quickly manipulate and use to help rapidly iterate how they might come to design a solution space. So, in effect, we have two powerfully different representations of design, of media for design. And I wanted to spell out these different capacities or dimensions in order to frame us as we go forward in the discussion. So while the innovation of the 3D models that we see on the left were more richly detailed and more precise, teams often relied on things much like this much messier and more imprecise, sketchier version of the same representation on a whiteboard. Why was that? Why was it that when they had these better representations, better visualizations, that they still reverted to the whiteboard and the sketches? Partly is the difference of these affordances that they needed in design media. So the BIM model was actually cognitively quite passive, that they were not as active in thinking through the problems of the building when they were looking at the three-dimensional model. Whereas on the digital model, on the whiteboard model, they actually had to actively engage with that model in ways. So when they were running meetings centered around the three-dimensional model, they would just kind of point to it. They couldn't circle it, sketch it, change it, move it. The capacities were not there to allow the team to do that rapidly. One of the reasons is the difference between the formality of documents and the informality of documents. Everything in the BIM model was seen as being having a legal liability. So once it was in the project documentation, then it could be used in a lawsuit. And in construction, this is a very present, ever-present concern. Whereas whiteboard models, even when they were photographed and brought into the project documentation system, they were always seen as just that. They were always seen as something that was an informal communication of the team, not documenting a design decision or a set of chances. In essence, they felt they were, what is the expression? They could cover their backs through using the informal media rather than the more formal media. And then finally, this ability to be able to rapidly iterate on the fly was incredibly important for these teams. And they got this from the whiteboard. They couldn't get this from their digital system. So when we're thinking about innovation within these kinds of teams, and is innovation new? Innovation is something that is novel. Innovation is something that's useful. When we have a medium change of an architectural blueprint that's changed after 2,000 years of use and a whole host of legal, contractual, social, industrial, educational practices around it. Those practices are quite sticky. So what we found is that when we're talking about innovation in this space, we have the three-dimensional models were great for leading to discovery. The paper and the whiteboard, though, were great for leading for solutions. So instead of thinking about one kind of medium that these teams would use, that would be the one-size-fits-all, that the real innovation was actually quite incremental, that they're still relying on two-dimensional plans and specifications, they're still relying on blueprints, they're still relying on sketches, but the models are helping them think through problems in new ways. Oh, okay, and here's my 2 minutes, I promise you, of totally geeking out. I think all the engineers would like hate this talk if I didn't do this. All the building engineers. So these 5 depictions are of the state of the level of design of three-dimensional models, and they have an engineering standard for it. So is it level of design 100 or level of design 400? So it's just how detailed are these three-dimensional models. In the first one, we see that it's simply the form or shape of the building, and that's often where architects start. By the last one, LOD 400, you're ready to essentially print out blueprints, if I may be casual with that language, from the three-dimensional model. So what's happened in this field is that there's cognitive flexibility early, and interpretive flexibility early in the process, when there's not a lot of project documentation. There's a lot of scope. Like when the project's wide open in the beginning, they can do lots of things and think of lots of solutions. But what's happened as we've moved the level of detail earlier and earlier into the project timeline, the amount of documentation has grown earlier in the project timeline, and it literally cuts into the interpretive flexibility of teams being able to make solutions and generate ideas earlier in the process. So we're seeing that it's not simply about how these teams are collaborating. It's literally changing the terms on which they collaborate, and that's where we see our problems. So here's my big takeaway, and I think it's a takeaway that's relevant for a whole host of data-driven analytics. That when you put a team of cross-disciplinary professionals, when you put together a cross-disciplinary team of professionals, the way in which they use abstractions and malleable media radically shape how they come up with design solutions. This is an innovation that we used. I wrote a piece about this in Pacific Standard magazine of an everyday innovation. So this is simply what you and I might call a blueprint, printed onto whiteboard. And this was done by the superintendent of the building. Now, there were the fancy 3D models being used in these buildings. There was fancy LiDAR, laser technology. But for his daily meetings with his crew, he wanted to have something that he could point to, draw on, mark up, and even more importantly, then erase and do it again the next day. So I think as we go forward in designing the ways in which teams work with, through, around, and sometimes despite data being brought into those teaming and decision-making processes, that we need to keep this in mind, that often it's the being able to erase that helps us get to great solutions generated by teams.